Hello everybody, my name is Abid Samouri, I'm your host, and this is the 13th episode of the Navigating the Cyberland series. Before I jump into the presentation, I would appreciate if you just indicate on the chat that you can hear my voice clearly and you can see the shared screen. Awesome, great. Thank you guys. The topic of today's webinar is going to be in-memory code injection, attacks, and detection. And I would like to draw your attention that this webinar is recorded and you can view all recordings, the previous one as well as this one, on the website app.livestorm.co /Axon-technologies. Something new we have introduced as of this webinar, there will be a certificate of attendance under the condition if you get 60% on the quiz at the end. So at the end of this webinar, after 1 hour to 1 hour and a half, I'm going to distribute a link to a quiz of 9 questions, true and false questions. And if you get 60%, you are entitled to receive a certificate of attendance signed by me and the CEO of the company. So stay tuned until the end of this webinar. Take your notes and make sure you pass the quiz. The agenda, the content of today's webinar is going to be like this. I'm going to talk about an overview of what code injection is and an introduction to code injection, and then define code injection in details. And then I will talk about 4 types of code injection techniques. There are many on the wild. There are more than 10, 12, and even more. But I'm going to explain 4 of the most common and most sophisticated ways. And these are classic DLL injection, PE injection or portable executable injection, process hollowing, and thread execution hijacking. These are 4 types of code injection in memory. And then we will jump into detection techniques, how to investigate loaded DLLs in memory, how to utilize and use the virtual address descriptor. What is the virtual address descriptor, the VAD, and how you utilize it to actually find hidden DLLs and unlinked DLLs. We will see how we can dump artifacts from memory pages on the hard disk and then investigate them. And then we will talk about permissions and how page permissions can reveal so much about the code injection attacks. So ultimately, when there is a malware on the system, that malware needs to run. Okay, a malware, no matter where it hides, how it hides, ultimately when it runs, it needs memory. So a running malware is always somewhere in memory. So by doing memory forensics, by analyzing what's going on in memory, ultimately you're gonna reach to that malicious code and you're gonna find it. So what is there in memory? What do we find in memory? Basically, in memory, the main thing is processes. Okay, when you look into memory, you see processes. Everything else is associated with process. So whether it's a network connection, network connections are operations performed by processes. Whether there are DLLs files, these are loaded by the processes. Processes have threads in them. There are sometimes structures, data structures by the kernel to manage processes ultimately and to manage the memory around processes. In memory, you can find stacks, buffers, pointers, etc. All of that will serve processes. So ultimately, when we investigate memory, when we do memory forensics, we are looking into processes. And a malware is somewhere in those processes. Now, when you look into processes, there are two possible ways to find the malicious code. Number one, the malicious code is running on its own process, on its own malicious process. And this was the topic that we discussed in the previous webinar. So if you go to the previous webinar, we have discussed tips and techniques to differentiate malicious processes from legitimate processes. However, in order to evade that, attackers sometimes inject the malicious code inside a legitimate process. So you look at all processes, you do not find anything suspicious, there is nothing malicious, yet there is a malware, and that malware is running inside a legitimate process. And this is where code injection comes in, and this is the very topic of today's webinar. So what is code injection? Code injection, in short, is when one process, whether it's malicious or not malicious, when one process writes a code into the memory address space of another process. So if you look at the right graph over here, this is one process. Okay, it has a starting address in memory and an end address. And then another process would allocate space inside that process and inject some code in it. Okay. Now, why would attackers do that? There are different reasons. For example, if you have an antivirus or any signature-based security tool that has rules, detection rules for processes, code injection can evade process-based rules. Also, you have privilege escalation. So, for example, if you are running on process A, for example, might not access certain buffers, certain variables, certain tokens, while process B has access to other buffers, other tokens. So if you inject your malicious code into process B, then that malicious code can have access to those buffers and tokens. Somebody is asking about previous webinars. I already mentioned the link at the beginning of this webinar, and also I'm gonna put it on the last screen of this webinar. So at the end, I'm gonna provide you the link for all the recorded webinars. But basically, it is the same link where you have registered for this webinar. So if you go to the registration page and then you click on Axon Technologies page, then you will find all the previous webinars. So let's talk about the first technique, which is the classic DLL injection technique. In the classic DLL injection technique, what is injected is actually a path to a malicious DLL file on the disk. So the malware or the attacker creates a DLL on the disk, okay, not in memory, on the disk, and then the attacker or the malware would inject the path of that DLL into the target process, and then that target process, with a certain trick, we're gonna see now what this trick is, will load at a later stage, will load that DLL from the disk into its own memory space, and then will run it as part of that process. But the injection itself, the DLL is not injected directly into the process. The path of it, the path on the disk is injected, and then it is loaded automatically at a later stage. Let's see the steps for classic DLL injection. Step number one, look at the graph over here, the malware process in red, okay? This is the malware process that ultimately is going to destroy itself and inject its malicious code into a legitimate process. So stage one or step one, it needs to search for a target process. And the way it does this is there are certain APIs or system calls that will give me a snapshot of all the running processes in memory as a chain in a chained list or a linked list, and then the malware process would navigate through this list until it identifies a certain target process. So let's say it's legitimate process number one. So it picks number one, and then it calls a function or an API called open process. Once it calls an open process, and then it passes the process ID, the PID, which is the last parameter over here. It passes the process ID. What's going to get is a handle to that process, and that handle is a pointer to that process. So it has now a pointer to legitimate process one. Once it has that pointer, it needs to create a space in the memory space of that process. And to do that, there is an API called virtual alloc. Virtual alloc allows the malware process to create a buffer or to reserve a space in memory in the remote target process. And you can pass to it different parameters. The most important parameters are the edge process, and that is the very handle to the target process, which we have received from the previous API called open process. And then it needs to pass the size of that allocated space, and the size is going to be exactly the size of the path of the DLL. Okay, so let's say it want to allocate like 50 bytes inside target process one, and then it needs to give it certain permissions. And the most common permissions for code injection is execute, read, write. Why is that? We need, first of all, the permission write so that we can write our code into the process. And we need the execute permission because ultimately we would like to execute that code. So execute and write are the two essential permissions for code injection. If you have write but no execute, ultimately your code will be written but not executed. And if you have execute but there is no write permission, you cannot actually inject your code. So you do virtual alloc, you have allocated space, as you can see here with the red box inside process one. So you allocate that. Once you have allocated and reserved that memory, now you are going to write something inside that reserved memory address, memory space. And what you are going to write is the path to the DLL. So the malware would create a DLL file on disk. Let's give it the path C temp directory, and let's call it mal.dll. This is our file on the disk. And with virtual alloc, we have allocated space. Now we're gonna use another API, and that is write process memory in order to write into that allocated space. And we will write the path, the ctemp mal.dll. And the way to write it, we're gonna call write process memory, and we're gonna give it few parameters. The process parameter is the very handle to the process, which is the same one we used in the previous call. And we're gonna give it a pointer to the allocated space, and that pointer was returned to us by the virtual alloc previously. And we're gonna give it the very string itself, the buffer that contains the ctemp mal.dll, and then the very size of that string, which is the same size, the 50 bytes in our example from the previous virtual alloc. Once you call this, now the target process has in it an allocated space, and then inside it there is the path to the DLL on the disk. Next, we would like to load the DLL and execute. And in order to do that, we have an API called the create remote thread. Why do we need to call this create remote thread? Because ultimately, our loaded DLL, in order for it to run, it needs to run as its own thread within the target process. So we're gonna create a new thread and then associate this new thread to the DLL and call the DLL to load. And once it is loaded, it's going to run automatically. So create remote thread is going to take the process handle, the same process handle we've been using so far, okay? And then it is going to call, if you can see the start address, this is very important parameter in the create remote thread, because the thread, I need to associate it with a function that executes. Otherwise, the thread does nothing. And the best function here that I would like to use is a function that is a standard in Windows systems, and this function is called load library. Load library is a standard Windows function that loads DLL files. So I will give the address of load library, and the address of load library in every process is a static address, by the way, so it can easily be obtained, and we will see an example at the end. So we get the address of load library and we put it as a parameter here, and then load library is going to load a DLL, but which DLL? So I need to pass the path to the DLL so that load library loads the DLL inside my path. So I'm gonna point with parameter, the LP parameter, I'm gonna give it the very memory segment that contains the path, okay? So I will give it load library, the address of load library, and then I will give it the memory segment containing the path. Once I call create remote thread, there will be a new thread now, and this thread will execute the function load library, and load library will load my DLL, and once it is loaded inside legitimate process 1, is going to execute the malicious code that is inside that DLL file. So here is a sample working code that you can get, and you can test it in your environment. You can see, first of all, I call open process, and with open process, I give it the parameter at the end, the PID. So the PID is the target process that I would like to inject code into, and then open process will return a handle called process, and this handle, the process handle, is what I'm gonna use in subsequent calls. Once I have the handle to the process ready, okay, I need to get the address of load library, because I'm gonna use it later on with create remote thread. So I call a function called get proc address, okay, and then I give it the name of the function load library A, and then I save the address of load library inside the parameter load library, and then I will save it to be used at the stage before the end, okay, with the create remote thread. Next thing, I need to allocate the space with virtual alloc. Okay, I need to allocate the space with virtual alloc. So I'm gonna call virtual alloc. I'm gonna pass to it the process handle process. I'm gonna tell it it is going to be read write. Okay, and I'm gonna give it the length of my DLL path. So the parameter DLL, the string strlen DLL, this is the length of the DLL path. So virtual alloc now is going to reserve this memory, okay, with this size, with the size of the path of the DLL, and then will return to me the memory address of that allocated space. Then I would like to write to that memory address using write process memory. Again, I'm gonna give it the process handle because I'm writing to that process. I'm gonna give it the memory address using the memory parameter. So write inside process, inside the memory address that I have just allocated with virtual alloc. What do I write? I write the DLL. The DLL is a string parameter simply containing the path of my DLL on the disk, okay? And I give it the length of that path. Once the path of the DLL is written, next step is to call create remote thread. Create remote thread in order to load the DLL and execute it. So create remote thread where inside the process handle that I have process, okay? And here I give it the address of load library, which is inside the parameter load library, and memory. And if you notice with virtual alloc, memory is the reserved space that contains now the DLL path. So load library is going to look inside memory, get the path, load the DLL that is pointed to by the path, and then run it inside the our target process. Okay, this is basically the classic DLL injection. If you have any question, please you can interrupt me and type it on the chat. Okay, let's move on to the next technique. Next technique is called PE injection. So in the PE injection, I'm not writing anything on the disk. I'm not writing a DLL and then I'm pointing to it. I am injecting an executable file, an exe file, directly inside the target process. Whenever you have a file that is .exe, this is the format of it is portable executable. Okay, the format of which is portable executable, PE. Whenever you have DLL, the format is DLL. So we have two formats for code, PE format, DLL format. PE is executable directly. Okay, you can create a process directly out of PE file. But with DLL, you cannot. DLL needs to be loaded within a process in order to execute the code in a DLL. So I create a memory inside my target process, and then I inject a PE file, a PE code, okay, like an exe code. So this will be like exe within a larger exe. You can think of it this way. So we have the target process that was initially an exe PE file, and then I'm gonna embed another malicious PE file inside the larger legitimate PE file. Okay. And in this case, the malware can copy itself fully inside this address space, and we will see something interesting later on when we come to the demo. We're gonna see how Metasploit Meterpreter does exactly this when it is injecting itself into another processes. Okay, and we're gonna see the attributes and how the new process looks like and so on. Yes, somebody is asking PID stands for process ID. Yes, absolutely. However, there is a challenge with PE injection, and this challenge is the base address of the code. Whenever you have a PE, okay, the PE has what is called the base address, and the base address is the physical address where it is located in memory, and then everything else is relative to that base address. So you have virtual relative addresses, okay, that are accumulating on top of the base address. But when you inject the PE, okay, from one malware process into another target legitimate process, the base address is going to change. And if you leave it there, your PE code, injected PE code, will not actually work because the addresses will be messed up. So you need to recompute the base address and then adjust all relative addresses of the function called within it relative to this new base address. Okay, now this is not very hard to do. There are certain routines and functions that you can simply traverse a certain table, address table, and then recompute it. Again, if we want to look into step by step how PE injection works, step one is exactly like with the classic DLL injection. You need to search for a target process, okay, and you're gonna use open a process API to get a handle to that legitimate process. And then once you have a handle, now you're gonna allocate a space in the target process. Again, exactly similar to the previous one, using the function of the API virtual alloc. Okay, so with virtual alloc, you can allocate now a new space, a new memory segment inside that process. The only difference now is the size of that allocated process. In the previous technique, the size was simply the size of the string of the DLL path, while in this technique, it's going to be the size of the entire PE code. Okay, so it's going to be generally a larger size, okay, a larger size. And also, we need the permission execute read write again. I want to point out that the function virtual alloc, we're gonna see virtual alloc in every technique, in every code injection technique, and virtual alloc is almost every process analyzer tool considered dangerous API. So whenever there is a code that is using virtual alloc, usually it's a red flag. Okay, that doesn't mean 100% every time there's virtual alloc it's a malicious malware, but usually it's a red flag. Okay, malware always use virtual alloc to play around with processes. So once I have the process allocated, once I have the memory allocated and reserved for me using virtual alloc, now I can write to that. Okay, I write to it using write process memory API, again, the same API we used in the previous technique. I'm going to give it a handle to the target process. I'm going to give it a pointer to the allocated space that I have received from virtual alloc. I'm going to give it the actual buffer to write, and this buffer is going to be the entire PE segment, the entire PE code, and the size of that PE code. And as you can see on the graph, I have now dumped or injected my PE inside legitimate process 1. However, once I do this, until now, my code, my PE code will not run because it's written there, but it needs something to trigger it. Again, just like in the previous technique, we can use create remote thread. So out of this new PE code, I want to create a thread that points to the main function of that PE so that it runs it and it executes. So I call create remote thread, and I'm gonna now, first of all, I'm gonna give it the handle to the target process, okay, the H process. And the start address, if you remember in the classic DLL injection, the start address was the address of load library. Okay, load library was the main function that I executed in that thread, and load library loaded my DLL. However, in this case, I want to compute the address of the main function inside the injected PE, and once I have that address, I need to pass it to create remote thread. Once I pass it, okay, the parameter now has no meaning. In the previous one, the parameter was the path of the DLL. Now I do not need any parameter because the main function will simply execute on its own and will do whatever malicious code that is embedded there. So in summary, if we would like to summarize the difference between a classic DLL injection and PE injection, the steps are the same. The only difference is with classic DLL injection, I am injecting the path to a DLL that is on disk, okay? While on PE injection, I'm injecting the entire PE executable code, okay? And in the classic DLL injection, I'm calling load library to load the DLL, while on the PE injection, I'm calling the main function of the PE of the injected PE. Now we have two more techniques that are very similar but different from the previous two. This one is called process hollowing. Process hollowing. And the main concept of process hollowing is to replace the content of a legitimate process entirely and replace it, to remove it and replace it with my malware code. So I'm not only injecting my code into unused memory space inside the process, I am actually emptying the entire code and the content of the legitimate process, stripping it away from its actual code and putting my own code inside it. Okay, and this is where the term hollowing came from. It has also another name called process replacement. Also, it's called run PE. Okay. So in the PE injection technique, my injected PE does not replace the original PE inside the process. Okay. While in process hollowing, I am fully replacing it. Okay. So deleting the original PE, putting my own PE instead. The way to do that, okay, the way to do that, step one is I create a new process. I create it from a legitimate executable file. So I run, let's say, Notepad, I run calculator, I run whatever application that is legitimate is going to create a process in memory associated with that application. So there will be like a process for Notepad if I open Notepad. So there is a process Notepad. However, when I created with a flag called create suspended, which means the new process is not going to run, but it's going to be loaded in memory, but it is in a suspended state. It will not run until I give it the instruction resume. Okay? because if I want to delete its content, I cannot delete it while it's running actively. It has to be in a suspended state. So I create a new process. I give it the flag create suspended. To create a process, I use the API create process. This is basically it. And it takes so many parameters. However, there are only two that we would like to focus on. The first parameter is LP application name. Okay, this is the path to the original exe file on disk. So this will be like C Windows notepad.exe, for example. And so it will create a process out of that exe file. And I need to give it the creation flags, okay, create suspended. So in this case, I will have a process notepad in memory that is in a suspended state. It's not running, but it is still in memory. Okay. Once I have that process in a suspended state in memory, I need to do something called unmapping. Okay. So I need to unmap the memory of the new process. There are APIs for that, the unmap view of section that will simply empty the content of that memory segment or that memory section inside the target process. It will empty it until I have simply a skeleton of a process, but there is really nothing to do inside it. Okay, so once I have that process in a suspended state, but in a very stripped state as well, now I will call virtual alloc. So I call virtual alloc, and then I reserve a large chunk of memory in that process. Basically, most of it is empty by now, so I can create a very large chunk, and I call virtual alloc. I will give it the process handle that I already have, the size of my code, the malware code, okay, and the permission execute read write. Okay, so once I allocate now a new space that is in a place of the emptied one, now I call write process memory, our typical function, to write our own malware code. So I call it, giving it the handle to the target process, and then I will give it a pointer to the allocated space, because I want to write inside that process, inside that allocated space or buffer that I have allocated with virtual alloc. And then the very buffer that contains the PE section is passed to it, so that it is copied and injected into the remote process along with the size of the PE section. Once I call write process memory, then I have my injected code inside a process called notepad. So basically, the process is called notepad. It came from notepad.exe, but there is nothing in it that is close to notepad. It is now the virus. It's now the malware. Who can tell me on the chat what should be the next function or API to call to complete the execution of that code? It should be easy by now. We covered on the previous two techniques. Anyone can recall it, which will be step 5 in process hollowing. Nobody. So I'm gonna reveal it. DLL file. No, there is no DLL over here. Okay. It turned out there is a new thing that I need to do before executing or running the code, and that is updating what we call the entry point. Every process has an entry point. An entry point simply points to the main function inside the process. And if you remember, um, yeah, thank you, set thread context. If you remember, um, we have emptied the content of this process, and that content included the main function, which was the entry point. Now, if we have our own code injected, it doesn't mean the entry point actually points to the new main function of the malware. It still points to where the previous main function used to be. And in order to update this, I call set thread context, okay, to actually update a certain part of the process. Once I update it, now I'm gonna call resume thread. So in order to execute now my code, all I need to do is call resume thread. Remember, the process is already in memory, okay? It's already triggered. It's already, it was suspended, okay? So in order for it to run, okay, in order for it to run, all I need to do is to resume the thread, okay? So my code is inside the main thread now, and I resume, by calling resume thread, the execution will start, okay? I do not need to call here create remote thread, because the thread is already created in the beginning, and it was created yet suspended, okay? So resume thread is going to actually make it running. Remember, when we created this process, let's call it notepad.exe, we created in a suspended state, okay? And if we resume it directly, the main function of notepad is going to run. Now we have replaced the code of notepad.exe with our own code. Now, in order to execute now our own injected malware, I only need to resume the thread. Okay, that is, so resume is the opposite of suspend. Because I have suspended it, it will remain in a suspended state, and it will not run until I call resume. Okay. The fourth technique is very similar to process hollowing. Okay. However, the only difference is, and instead of creating a new process like notepad.exe or calculator.exe, okay, I'm going to find a running process, an already running process, and then I'm going to suspend that process. All right, I'm going to suspend that process. This will give me the advantage of not generating a lot of noise about creating processes. So if there is somebody checking every created process, then simply I'm not messing around with creating new processes. I'm only injecting inside already running processes. And this technique is also called suspend, inject, and resume, SIR or SIR. Okay. So how it works? Very similar to process hollowing. The first thing I need to do is I would like to open the thread inside that running legitimate process. Okay, so open a thread so that I have a handle to the thread, to the main thread and the target process. Ultimately, I want to have a handle to the thread, not only to the process. Why? Because I'm gonna suspend that thread. While in the classic DLL injection and P injection, I did not connect to any thread. I simply created, using virtual alloc, I created memory inside the process without messing around with any thread that's already running. While in process hollowing and thread execution hijacking, I am messing around with the main thread. Okay, so I get a handle to a thread that is running inside that process, mainly the main thread. Okay, once I have that handle, I'm gonna tell it, I'm gonna command it to suspend. So I'm gonna call suspend the thread. I'm gonna suspend that thread. Now, because it is in a suspended state, I can simply replace the code of it. Okay, I can simply replace the code and the content of it with virtual alloc. So with virtual alloc, the address now is going to be the very address of the thread um, itself. So I'm forcing it inside a certain thread with virtual alloc. Then I'm gonna inject my code using write process memory. Okay, in the same way we use write process memory to inject our code in the previous techniques. And once I have my code inside now, I'm gonna update the entry point just like I did with process hollowing using set thread context. And then all I need to do now is resume a thread so that my malicious code runs. Okay, so any question, guys, so far on the techniques of code injection in memory code injection? Good. So how do we investigate now DLLs? Because DLL injection is one of the common injection techniques, one thing we need to do when we do memory analysis and when we do process analysis, if we did not find any suspicious processes, we can investigate legitimate processes now and try to find suspicious DLLs loaded into legitimate processes. Okay. The way this is done is in memory, every process has something we call a process environment block, PEB. Okay. And the PEB contains some metadata about the process. It contains the path to the executable, to the process executable on the disk. It contains the command line used to launch the process. So if there are any parameters, options, etc., etc. It contains the current working directory from which directory it was called. And then the PEB contains loaded DLLs. So if we investigate the PEB of every process, I can see all the DLLs that have been loaded by that process. And the PEB contains those DLLs in different lists. Mainly it has 3 lists for the DLLs. Okay, the same DLLs, but ordered differently in each list. So the first list contains the DLLs ordered according to their position in memory. So whatever comes first appears first in the list. Whatever comes next in memory appears next on the list. The second list contained the DLLs, loaded DLLs, but ordered according to their loading time. So the DLL that was loaded first when the process ran is ranked higher in that list than DLLs that have been loaded later on. The third list contains DLLs ordered according to their initialization time. So maybe DLL-A was loaded first, but DLL-B was initialized first, okay? So the third list order the DLLs according to their initialization times. So if you use volatility, just like we explained in the previous webinar, we have a command called DLL list, okay? And it will simply print the list of all DLLs associated with every process or with a single process that you specify. Once you have the list of DLLs, loaded DLLs, try to search for any suspicious DLL names, okay? Something that looks unusual, okay? Like the one I have mentioned here, K6NVLQ8Z.DLL, okay? This is tip number one. Tip number two, look for DLLs that have common names, normal names, seemingly innocent names, but loaded from strange directories. For example, kernel32.dll should be running from C Windows System 32, okay? But if you see it running from C temp kernel32.dll, this is a big red flag, okay? That this DLL is actually malicious. Also, watch out for DLLs that change or alter security settings on your system. For example, the SFC OS.dll can disable Windows file protection. Okay, so if you see a process loading this DLL, it's a red flag. Doesn't mean it's absolutely malware, but it's a big sign. So you have to do enough investigation now why that process actually is loading this DLL to disable Windows file protection. The same with pstorec.dll. This DLL can extract credentials from Windows protected storage in memory. Again, if you see a process loading that DLL, it's a red flag. You need to do more work, more investigation. Also, watch out for out of context DLLs. For example, if you see a process notepad or a calculator, okay, loading a DLL with networking capabilities like WS232, like WinSock32, these DLLs are usually for network connections. I would expect Firefox and the Internet Explorer or Outlook to load those DLLs. But if I see a notepad or calculator loading them, this is a red flag as well. There is something suspicious here that I need to investigate. So these are great tips that you need to keep in mind when you investigate loaded DLLs. However, I told you that loaded DLLs, I can enumerate loaded DLLs by checking the process environment block, okay? And this is how DLL list command in volatility works. It checks the PEB block. However, PEB, the process environment block, is editable. Anyone can edit it and anyone can modify the entries in it. So sometimes malware, they would load a malicious DLL and then they remove its name from the PEB. So you issue DLL list, you don't see anything suspicious, yet the suspicious DLL is there in memory. Okay, and many conventional tools cannot detect DLLs that have been removed from the process environment block, including Process Explorer, Process Hacker, Volatility DLL List, List DLLs.exe. All of these tools will not detect any DLL that have been unlinked from the PEB. So where do we check and how can we investigate unlinked DLLs? The way to do it is we have something called virtual address descriptor, VAD. Okay, and virtual address descriptor is a structure that is maintained by the kernel by memory management. Okay, and it is not editable by any user space process, unlike the PEB. And the VAD, we'll talk about it in a while, contains every time you load a DLL inside a memory segment, that memory segment is registered in the VAD along with any file that is associated with it. So the virtual address descriptor is like a tree, okay? And the nodes of the trees, of this tree, contains information about allocated memory segment. So each time you do virtual alloc, okay, to allocate a memory segment or a memory page, okay, there is an entry that is being created in the VAD, okay? And that entry contains the starting address of that page, the ending address of it. If there is any file that has been loaded into that address space, what is that file, okay? And if you enumerate all the mapped files in the VAD, and then you see DLLs, and you see some DLLs not listed in the PEB, that means that DLL is most likely unlinked from the PEB, okay? So VAD is a great source, is a great place to look into to see, again, any reference to DLLs or any reference to files on disk. Volatility has few commands for VAD to actually investigate VAD. It has 4 commands: the VAD info, VAD walk, VAD tree, and VAD dump. VAD info provides detailed information about all the attributes and the sections of the VAD. Okay, it will tell you entry 1, starting address is this, ending address is that, what is the attribute, what's going on inside it. VAD walk simply will give you a summary of the tree, okay, with basic information. VAD tree is like VAD walk, but visually it's hierarchical, so you can see the tree. While the last one, VAD dump, which we're gonna do a demo in a while, is the most powerful among them, which can actually dump the content of those memory segments into your hard disk for later investigation. Okay, so I'm gonna now move to doing few demos. Okay, the first demo I'm gonna do is related to Meterpreter. Any one of you who has worked with Meterpreter or Metasploit and Meterpreter in particular can know that Meterpreter relies on, great, thank you, Lubin, relies on a technique called reflective DLL injection. We talked about classic DLL injection, and there is reflective DLL injection. Reflective DLL injection, in short, if you recall in the classic DLL injection, we injected a path to the DLL. In reflective DLL injection, I inject the DLL directly into that memory space, okay? And then I inject it in a way that is self-mapping, so it does not need load library or any other APIs to actually initiate it and run it, okay? So Meterpreter uses this technique. And just like I said, you can use volatility DLL list to list the DLLs, okay? This is one way, and investigate them. You can use the VAD info also to investigate. The greatest sign of code injection is the following. It is a memory segment that has read, write, execute all at the same time, okay? This is the greatest tell sign of code injection. So I created here okay. I have a multi-handler running on my Kali Linux, okay, waiting on this IP address and port number. I have already created an exe file with Meterpreter in it, and I moved it already to Windows 7 over here. Okay. This is my Meterpreter. So I'm gonna run this Meterpreter executable file. Okay, I should have a session that is opened over here. Now, it's session 3. If I do get process ID, this is the process ID that Meterpreter is running as right now, and I do PS list, and then I check 326, okay, over here, sorry, 3264, 3264, I'm gonna see my exe file, and this is very, very, it raises suspicion easily, okay? It raises suspicion easily. Now, Meterpreter is not injected into any legitimate process. It is running in its own suspicious process, okay? In order to inject reflectively Meterpreter as a DLL inside a legitimate process, I have the command called migrate. So migrate, and then I'm gonna pick a process that is legitimate, so that Meterpreter is going to inject itself into that process. And I'm gonna pick explorer.exe. Explorer is the one that handles the desktop in Windows, and it has the process 2448. So migrate to 2448, and successfully migrated. So if I do now get PID, Meterpreter now is inside 2448. Okay. So if I delete this one, if I stop this process, okay, and I delete this file, I still have my Meterpreter running, and it will not be affected as I am running inside the Explorer now. So I can delete it, I can stop the process, and if somebody is looking at all the processes, they will not find any suspicious process, while I have my Meterpreter code inside a legitimate code that is explorer.exe. So if I go to Windows 7, if I am investigating a Windows machine, okay, live means not in memory dump, I have a tool called Process Hacker. Process Hacker simply will give me a list of running processes along with a lot of information, unlike the processes that you see here. Okay, it will not give you much information. Process Hacker a lot of detailed information about running processes. So if I investigate explorer.exe, this is explorer.exe by the way. If I investigate explorer.exe, okay, remember I'm not looking at anything related to the process of interpreter. Okay, so I'm not looking at it's not the same as Process Explorer. Process Explorer is also good. Okay, Process Explorer from sysinternal is also another great tool. Okay, so it's a matter of preference, which one you like. So if I'm investigating explorer.exe, which is a legitimate process, by the way, and I look into the memory of it, these are memory segments that have been assigned using different system calls at different stages, okay, virtual, alloc, or not. And if I sort by protection is the permission. We can see that, for example, some pages have read, write, read, write, okay, write, read, write, and so on, okay. If I sort and then I go down, these are all read, for example, they have read permission, read, write permission. If I go down, read, execute permission, okay, write permission. If I check in the middle over here, there is something that is suspicious here. We have read, write, execute. Read, write, execute, read, write, execute, read, write, execute. This is the greatest still sign of code injection. Because remember, a memory segment that is executable, it should not be with write permission. Okay? So it should only execute. And the memory segment that has write permission where you can write to it, it should not execute. For code injection to be successful, you need execute and write at the same time. Okay? So if I double click on one of them, I can find there is some content in it. Okay? Some content. If I check, for example, this one, there's also some content in it. I can see there is TCP IP even here. If I check this one here, I can see that this, who can tell me when something starts with MZ, okay, and then after a while you see this program cannot be run in DOS mode. What does it tell you? Anybody familiar with this signature? Start of executable, PE, exactly, 100%. So I have here, or DLL, by the way, DLL has also the same thing. So that means I have an executable code in a memory segment inside the explorer.exe. And that is, by the way, the interpreter. So interpreter creates memory segments with read, write, execute. Okay. So when we did the migrate, okay, if you recall the migrate I did here, so it's called virtual alloc. Okay. Just like we studied in the beginning of this webinar, virtual alloc with permissions, and then it copied the PE of the interpreter inside it, inside those segments. This is the greatest tell sign of code injection. If you are investigating a memory dump, okay, a memory dump, I have taken a memory dump of this system while interpreter is running, okay, and I called it interpreter.draw and I moved it to Kali Linux. So if you are investigating a memory dump, okay, you can use volatility now, okay, and you can use a command that's called malfind. Malfind. What malfind does is it analyzes the memory segments and basically it checks for sign of malicious activity. And the biggest sign it checks is pages or memory segment with read, write, execute. So if I do malfind here, so this is basically the memory dump, okay, and the profile, and then I have given it 2448. This is the PID of explorer.exe. So I'm checking explorer.exe and I want to see what it finds in explorer.exe. And it finds exactly what I found using Process Hacker. So I found this, for example, this page, okay, execute read write that start with MC. So it gives me that it will dump the very beginning of that memory segment, okay. If I want to extract those memory segments, okay, I can use the vad dump, okay. If you recall the vad dump that I have mentioned here, okay, you can use them to extract all the memory segments from that process. And then you can even investigate this further. And just to show you how vad dump would work, we will look for some artifacts. We will see how you can actually use vad dump to extract memories, and then you can search them. And to do that, I'm gonna do a demo on Gmail. So what I can do is just, this is for the sake of the of understanding vad dump, okay. So I have here a memory dump of Windows 7, which I called Firefox 2.raw. And in it, I opened Firefox, okay, went to Gmail, signed in, okay, I signed in. I tried to sign in with my email. However, I did not enter the correct password. I simply entered some random password. Now that random password ultimately that I have entered, and then I click next, is going to be in one of the memory segments inside the Firefox process. So if I create a memory image, okay, that password is ultimately somewhere there. Then I move this this memory image to Kali, okay, and then it is right here, Firefox 2.draw, okay. And if I check Firefox.2, I check the processes in it. So I have this image with the profile, and then I'm simply listing the processes and getting the PIDs of Firefox instances. I have multiple, okay? And then I can do that dump on each of these processes, okay? And in order to do that dump, it's simply very straightforward. You take the process ID, okay? You take the process ID. You take the process ID and you give it the command, of course, after the profile, you give it the command var dump and a directory, okay, where you want the dumps to be stored in, and then the process ID, okay, and then it will extract all the pages and dump them there. I have already done so already in order to save times. Because I have 7 processes, I created 7 directories inside the Firefox directory. Actually 8. Okay, sorry. 7. That was an older one. Okay, and then I have that dump for each one of these processes. So if I go to 1, these are the dumps of all the pages. So imagine you can do the same for explorer.exe, and then you will find interpreter inside one of those pages. Okay. Now, can I find the password in here? Sure, it's very easy. I can do strings, okay, for everything that is here. Okay. So this will extract all the strings on all the files, and then I can grep for my password. And if you can see here the line identifier, this is the email address, okay, the email address, okay, and then the password is here. This is the password that I have printed. You can only see the Google page. Can you guys see the Kali page? The Google page is on Windows 7. I've already moved to Kali. Yes. So Khalid, maybe your network is hanging or something, or very slow. But anyways, so what I wanted to show you guys is if I dump the Firefox process, okay, ultimately the password is stored there. In the same way, if I dump explorer.exe, ultimately my interpreter is going to be there. Okay, so if I know there is a memory segment that is read, write, execute, I know its address. This is, by the way, the address of the page that is exactly shown by the VAD information, VAD info. So if I do VAD info over here, okay, this is VAD info. The VAD info will give me the start address and the end address. So if I have a doubt about a certain page, I dump it, and then I go to it, I open it with the starting address and end address, and then I can analyze the dump of it. I open it in hex editor, and then I can analyze it. Okay. I believe that's it for my webinar for today. Okay, I really appreciate your attendance, guys. I'm gonna send you the link to the quiz in a while, but just for the person who asked for the recordings, this is the link for the recordings. It's app.lifestorm.co /Axon-technologies. Okay, and then you can find all the 12 recordings, and including even the 13th one, which is this one, which is going to be directly uploaded after this webinar. I'm gonna paste it here. Okay, so here is the link to the quiz. Okay, the quiz is timed, so in 15 minutes. So I'm gonna give you guys 15 minutes, and I hope within, it won't take more than 15 minutes, by the way, in any case. So here is the link to the quiz. So I'm gonna expect answers within 15 minutes, and then any results or response that comes after 15 minutes from now will not be counted. Okay. So finish the quiz. Write your name in the beginning. There is question number 1 where you type your name as you would like in the certificate of attendance to be, and try to submit it within the next 15 minutes. Okay, 1 second. Let me do settings. Okay, 1 second, because the time is totally wrong. Okay, 1 second. Okay, can you guys update now or refresh your pages and tell me if it is resolved now? Resolved. Okay, yes, working. Okay. So with this I conclude, guys. Okay, you have my email address. If you have any question, you can contact me by email. Okay, and anyone who's gonna have 60% on the quiz within the next 15 minutes, we will email him a soft copy, email him or her a soft copy of the certificate. I usually don't send the PowerPoint slide itself, but you have access to the recording. Once you access the recording, everything is there. Okay. So thank you, guys, and good luck with the quiz. Thank you all. Good luck. Bye-bye.